Now, back when we first considered continuous data, I said that if there is an infinite number of outcomes, then the probability of any one of them occurring must, by definition, be 0. And perhaps that didn't sit quite right in your head, but we've got a bit more proof now that we're working with integrals. We've seen that we can look at the area under the PDF, and the size of that space is actually equal to the probability of that range of outcomes occurring. And so then it makes sense that if we wanted to find the probability of a single outcome, we would have to take a very, very thin slice, and the slice has virtually no width, and so therefore it's going to have no area. And that's better proof now for why that definite integral is 0. And in fact, when we first considered integrals, right back in chapter 4, we looked at the fact that a slice of 0 width would have no area, and in fact would have a definite integral of 0. So all of that now makes a little bit more sense. Now, when you're working with percentiles, you can use the same strategy as we looked at with quartiles or the median. So two different strategies we have now, because we've learned how to work with the PDF, the probability density function, or the CDF, the continuous distribution function. Now, a different strategy for each one. If you're looking at, say, the 50th percentile, that's the halfway point of the median. But remember, it's not the halfway point of the x values, it's the halfway point of the probabilities. Okay, that's an area that you could mess up. So with our example with the chook, we started with the CDF. Remember, we reasoned that if we knew the area of the inner circle and the outer circle, we came up with a formula for that. And in fact, we said that f of t was equal to x squared, let's put it in terms of t squared on 36. Now, the probabilities are lined up here on the y-axis when you're looking at big F of t. And so the strategy here really is just to say, well, let's let big F of t equal a half. And to do that, you're just drawing a line across and down and finding the associated x value that gives you the probabilities up to the halfway point. Now you'll notice that wasn't halfway along the x values, it was nowhere near 3, because a circle with radius 3 was nowhere near half the area. A circle with a radius of this is going to have half the area. Now, if you want to go ahead and let the CDF, or big F of t, equal half, that's effectively what you're doing. And the working is quite straightforward. We've already seen this. You would just let t squared over 36 equal a half, and so then t squared is 18, and t was the square root of 18, which we can write as, 3 root 2. Okay, that was quite straightforward, but now we have another method here. We can work with the PDF. Why would you want to do that? Well, perhaps you haven't figured out what the CDF is and you're starting with this one. We know that the area underneath the PDF gives us the probabilities of a range of outcomes occurring. So really we just need to move our x around to find the triangle here that would have an area of a half, because we know that the entire area of this big triangle is 1. So we want a triangle with an area of a half, and that's what this working shows. Find the definite integral from a, which is your lower bound, which in this case was 0, up to x, which we don't know what that is yet, and let's integrate little f of t, that's our PDF, with respect to t, and let it equal half, because we're looking for that 50th percentile. So here the working, our little f of t was the integral of this, which was t over 18. If we wanted to let it equal a half, we'd have to say, all right, we're going from 0 up to x, and we're integrating t over 18 with respect to t, and we want that to equal a half. Now we've seen the working for this, but just to continue it again with the picture so that it really makes sense, we're finding then the definite integral here, x, down to 0, and we're letting it equal a half. So of course here we would have x squared on 36 equals a half, which is the exact same working that we've got over this side, and we can see that x is going to need to be 3 root 2. Now whether you're working with x or t, the strategy is the same. A lot of people prefer to use x as something that can move around, whereas we're on the t-axis. Other people stick with both of them being x's. It's up to you to some extent. Now if we were looking at the 90th percentile, then remember we just want the 90th percentile of the probabilities. So in theory, we could just go to the CDF, look at where we get to 0.9, and let big F of t equal 0.9. In other words, go across and down and find the x value that that lines up with. The same sort of strategy over here would be to say we want a triangle that has an area of 0.9. So you can figure that out here and you'll end up with the exact same x value in both cases. Now don't forget that if we're solving definite integrals and we don't have an equation or a formula for this little f of t, we can often just use area formula to come up with the same thing.